Hello and welcome to the third review session for Calculus 1. Again, I apologize for the delay. It's some time-sensitive work that I needed to get done and couldn't quite get finished before 8:30. But here we are. It's time to do some calculus. So I want to start out by reviewing some of the activities that we've done in class recently, because they incorporate a lot of really important concepts from the course. And as always, if you have any questions, put them in the chat, send me an email. I'm happy to answer any and all questions. So let's get started looking at this area accumulation functions activity. So we're given a graph of a function called little f, and we are asked about this function capital F, which is the integral of little f from 0 to x. I think it's really helpful to have an example in mind as you're thinking about these kinds of functions. One example I like to think about is imagining that the little f function is telling you about the rate at which snow is falling. So maybe this is time in hours, like midnight, 1 a.m., 2 a.m., and snow is falling at a rate of 1 inch per hour, and then it is snowing more and more up to 2 inches per hour from 2 a.m. to 3 a.m. And then, the snow starts slowing, and then I guess at 5 a.m. snow starts melting? I don't know. It's not perfectly realistic, but that's the idea. So then what is the capital F function telling you about when you integrate the rate of snowfall from 0 to x? That's telling you about the amount of snow that has accumulated on the ground since time 0. Another common example is we might think about position and velocity. So we'll probably think about this little f as being velocity, and when we accumulate that velocity from 0 to x, what that tells us is your displacement from time 0 to time x. How far you ended up away from where you started. I like to think of this as the little f, which is the velocity. That's what your speedometer is telling you as you're driving down the highway. And the integral from 0 to time x is telling you, well, that's what the trip odometer would read. If you reset the trip odometer to 0 miles at time 0, then at time x, this integral is accumulating your velocity to figure out how far you've gone. So it's telling you, that's what the trip odometer is telling you. I'll come back to that analogy when we look at the fundamental theorem of calculus, part 1. Okay, so capital F of 0, that's the integral from 0 to 0. It's asking about the area underneath this curve from x equals 0 to x equals 0. Well, there is no area there. That integral is 0. Capital F of 1 is the integral from 0 to 1. That's the area from 0 to 1. That's a 1 by 1 square, so the area is 1. F of 2, capital F of 2, is this area, which looks like 1, 2, and a half. So that's 2.5. And then F of negative 1, it looks like the area is 1, but actually the integral is negative 1. It's because we're integrating backward from 0 back to negative 1. And when the bounds are in the wrong order, we should switch the bounds to put them in the right order, and switching the bounds introduces a minus sign. Now, when the bounds are in the right order, that integral is positive 1, but we also have this minus sign, so it's negative 1. You should think of this in terms of one of the examples. For velocity, this function, capital F, is telling you where you are relative to where you started at time 0. So if I plug in negative 1, we're asking, where were you an hour before time 0? But if your velocity is positive this whole time, meaning you're moving forward, then an hour ago you were 1 unit farther back, so negative 1. In terms of the snow example, if it's been snowing this whole time, how much more snow was on the ground at time negative 1 than at time 0? Well, actually there was 1 inch less of snow at, let's say, 11 p.m. than at midnight. So with either example, we see it should really be negative 1. Okay. Shaded and find the area represented by capital F of 3 minus capital F of 1. Well, capital F of 3 is this area. Capital F of 1 is this area. So when I subtract the purple area from the blue area, what I'm left with is this area. It's the area between 1 and 3. Okay, find a formula for capital F of x between x equals 0 and x equals 1. Well, the formula is just capital F of x equals x. How do I know that? Well, when I plug in 0, I'm supposed to get 0. And when I plug in 1, I'm supposed to get 1. This formula certainly does that. Another way to see that, well, I could even think about values between 1 and 0. What if I pick a value x? Capital F of x is this area from 0 to x. That's a rectangle with the width of x and a height of 1. So the area is x times 1, which is x. So just to expand that out, capital F of x, let me remind you, is the integral from 0 to x. And we can see that that gives us an area of x. Give two values at which f of x equals 0. F of 0 is 0. We've already discussed that. And then the point is, we've got all this positive area, but once we end up beyond 5, the area is below the x-axis, so it counts as negative area. And at some point, if you continue far enough off to the right, you'll accumulate enough negative area to cancel out all of this positive area. So how far out to the right do you have to go? Well, from 0 to 5, how much area do we have? I see 1, 2, 3, 4, 5, 6 and a half units of area. 6 and a half. And then I have this negative 1/2 here, so I'm back down to 6. And then every unit I go to the right, I'm going to decrease by 1. So if my total area, my net area is 6 at x equals 6, then I need to go 6 more units to the right. So by the time I'm at 12, all of the positive area here has been wiped out by the negative area over there. Which is larger, capital F of 3 or capital F of 4? It's capital F of 4. It's a little tricky. You're tempted to say 3 because this value is higher than that one, but if you actually calculate capital F of 3 and capital F of 4, you'll probably compute both of these correctly. This area is 1, 2, 3, 4 and a half. And capital F of 4 tacks on this area. That's another 1.5, which brings it up to 6. So capital F of 4 is bigger because it has accumulated more area. Specifically, it has accumulated all of this additional area. Again, I think it's helpful to think about this in terms of an example like snow falling. Capital F, remember, capital F is how much snow has accumulated on the ground. So they're asking, is there more snow on the ground at 3 a.m. or at 4 a.m.? Well, from 3 a.m. to 4 a.m. it is still snowing. So there's more snow on the ground at time 4, or at 4 a.m. Now, which is larger, F of 5 or F of 6? It's going to be F of 5. Because as we move from 5 to 6, we're going below the x-axis. So this negative area here actually decreases the net area. In terms of the snow example, at 5 a.m. it stops snowing and the snow starts melting. So is there more snow on the ground at 5 a.m. or at 6 a.m.? Well, at 5 a.m. there's more, because by 6 a.m. some of it has melted away. Alright, so when is f of x, big F of x, increasing? And again, if you think of this as the amount of snow that's accumulated, when is the amount of snow on the ground increasing? It's whenever it's snowing. The amount of snow on the ground is increasing. Once the snow starts melting, then the amount of snow on the ground decreases. So whenever this is positive, whenever the graph is positive, little f, then capital F is increasing. So negative infinity to 5. F has a local extremum at x equals 5. Is it a maximum or a minimum? If you think of the snow example, this is easy. It's been snowing all night, and then I guess the sun comes up and the snow starts melting. So that is a maximum. The moment when it stops snowing and then the snow starts melting, that is a maximum. Really what's going on here is the relationship between capital F and little f can be described this way, but it's also true that the derivative of capital F is little f. That is the content of the fundamental theorem of calculus part 1. So you've been asked questions like this much earlier in the course, because essentially we've given you the graph here of the derivative of big F, and then we're asking you questions about big F based on its derivative. So when I see the graph of a derivative go from positive to negative, that tells me that the original function, capital F, is going from increasing to decreasing. When a function goes from increasing to decreasing, that's a local maximum. Capital F is increasing at both x equals 1 and x equals 2, whereas capital F increasing faster, it's increasing faster at time 2. In terms of the snow example, we're asking when is the amount of snow on the ground piling up faster. What happens? It's faster up here because it's snowing at a greater rate, 2 inches per hour instead of 1 inch per hour. And again, you're looking at the derivative of capital F. That derivative is greater here. It's got a bigger y value, so capital F is increasing at a faster rate. So we have a new graph here. Capital G is the integral from 4 to x of little g. So capital G of 4 is 0 because it's the integral from 4 to 4. There's no area. Capital G of 10 is the integral from 4 to 10. That is this area. That's a triangle. So the area is 1/2 base times height. The base goes from 4 to 10, so it's 6. The height goes from 0 to 4, so it's 4, and that comes out to 12. G of 12 is this, where this area is negative. Now we could take this area and subtract this area, and I think that's what we'll do. But another way to do this would be to notice that this area exactly cancels out with this area. So the result is just the area of this triangle. But we already know that this triangle has an area of 12. So if we subtract off that area, which is 1/2 times 2 times 4, we get 12 minus 4, which is 8. Lastly, g of 0 is the integral from 4 to 0 of little g of t. Now these bounds are in the wrong order. The bigger one should be on top. So we can switch the bounds and insert a minus sign. Now the integral from 0 to 4 is this area, but negative because it's below the x-axis. We're looking at a circle of radius 2. So a circle of radius 2 has an area of pi times the radius squared, but it's only half of a circle. So we should take half of that. And I forgot to make this negative. This minus sign was coming from here. But this integral also gives us a minus sign. So there are two negative signs, one because we're integrating backward and another because it's below the x-axis. So it actually comes out to a positive 2 pi. Where is capital G of x increasing and decreasing? Well, once again, the derivative of capital G is little g. We're looking at the graph of the derivative. So if we're looking at the graph of the derivative, where is the original function capital G of x increasing? Well, when the derivative is positive. So negative infinity to 0 and 4 to 10. And capital G is decreasing where its derivative is negative, which happens on 0 to 4 and 10 to infinity. Okay, local extreme values. Extreme values are going to happen at critical numbers. Critical numbers are places where the derivative is 0 or undefined. But remember, if we're thinking about capital G, the derivative of capital G is little g, so we are already looking at the graph of the derivative. That means the critical numbers happen here, here, and here. Just places where the derivative has a value of 0. Not places like this. Because this is a place where little g prime is undefined. But that's the second derivative of big G. We're supposed to be looking at the first derivative of big G. Okay, so my critical numbers are 0, 4, and 10. And are these local maxima or minima? Well, at 0, the derivative goes from positive to negative. So capital G goes from increasing to decreasing. That's a local maximum. The same thing happens at 10. Whereas at x equals 4, the derivative goes from negative to positive, meaning that capital G goes from decreasing to increasing, which is a local minimum. On the interval from 0 to 12, whereas g of x increasing fastest, it's increasing fastest at time 8. Because that's when its derivative is the largest. All right, I want to look at the graphical fundamental theorem of calculus activity because it's very similar. It uses the same function, in fact. And the point we've been making is that the derivative of this function, of this accumulation function, is just f of little x. Sorry, little f of x. Okay, capital F of 0, we already computed that in the previous activity. That's 0. F prime of 0 is little f of 0. So I'm just looking at the y value on this graph. That y value is 1. And then the second derivative of big F is the first derivative of little f. Right, I'm just adding one more prime to both sides of this equation. So that's the slope of the graph I see here, and that slope is 0. Capital F of 2 is the area here, which is 2.5. F prime of 2 is this y value, which is 2. And f double prime of 2 is the slope here at x equals 2, which is not defined. Capital F of 5 is 6.5. That is all of this area. Capital F prime of 5 is the y value here, which is 0. And f double prime of 5 is the slope here, which is -1. Find a formula for capital F prime of x between x equals 1 and x equals 2. Well, remember, capital F prime is little f. So I'm looking at this part of the graph. Well, that looks like the line y equals x. Plug in 1, I get 1. Plug in 2, I get 2. Yep. So I know that capital F prime of x is x. At least if x is between 1 and 2. If we wanted, we could write down a whole piecewise function. You know what? Let's do that, just for fun. So the piece that we worked out is that it is x if x is between 1 and 2. Now if x is less than 1, my y value is just 1. Between 2 and 3, the y value is 2. And then over here, this is a straight line with a slope of -1, and it has an x-intercept of 5. That means it's got to be 5 minus x. So that is capital F prime of x. Now we could find a formula for capital F of x between x equals 1 and x equals 2. I know that the derivative of capital F is x. That means that f of x has to be an antiderivative of x, so it has to be 1/2 x squared plus some constant. But it would be wrong if I just left this as a plus c. Because plus c means that you could put any constant there and it's an answer. That's not the case here. Because we have some actual values we could look at. For example, I know that capital F of 2 is supposed to be 2.5. So 2.5 is 2 plus c, which means c can't be any constant whatsoever. It actually has to be 1/2, which means that f of x is 1/2 x squared plus 1/2. I also know that capital F of 1 is 1. So if I used that instead, I'll get 1 equals 1/2 plus c. So once again, c is 1/2. Of course, I have to get the same answer. Now we're asked to sketch capital F and its derivative, but we already know that the derivative is little f of x. So the graph is just the same graph that we were given. The graph of capital F of x is a little more interesting. So I know some values. So why don't I plug those values in? F of 0 is 0. F of 2 is 2.5. F of 5 is 6.5. I guess on the previous activity we computed that f of -1 is -1. We already know that f of 1 is 1. F of 3 would be this area, which I can see is 4.5. F of 4 is 6. F of 6 is 6. Now I should connect all these together all the way up until time 1. This derivative graph is constant, which means that the accumulation function should be increasing at a constant rate. what we're doing is we're graphing a function whose derivative is this graph. So I need a function whose slope in this part is a constant 1. And in this part, I need a function whose slope is a constant 2. Now in this part, well, I guess we actually found a formula for capital F of x. Because of this 1/2 x squared, this is a parabola. I'm just going to kind of smoothly fit a curve in there, but that's part of a parabola. And from 3 onward, the derivative is a straight line, which means that an antiderivative, which is what I'm graphing here, is going to be a quadratic. So again, I should try to sketch a parabola, or a piece of a parabola that fits these points. So if you wanted to repeat this problem, not just for this one portion of the graph, but for each portion, you could get a piecewise equation describing capital F of x. And if you plotted it, it would look like this. Right? So we said it's snowing, and then it's snowing a bit faster, and then the snow slows down, and then the snow starts melting. What we've graphed here is how much snow has accumulated on the ground. The amount of snow is increasing, and then it's increasing even faster, and then it reaches a maximum, and then it starts to decrease just a little bit. So again, this is an antiderivative of this. This is the derivative of this. Okay, I want to move on to the analytical fundamental theorem of calculus activity. I did this one in class today. You might have seen it in your class previously. But I'll run through this pretty quickly. So we're supposed to find a formula for capital F of x, which is the integral from 2 to x of t cubed dt. How do I evaluate a definite integral? I find an antiderivative, and I plug in the upper bound, and I plug in the lower bound, and I subtract. And make sure to do it in that order. Upper bound first, lower bound second. So I get 1/4 x to the 4th minus 4. Now we're asked to find f prime of x, which means differentiate this thing that we just computed. When I differentiate this, I get x cubed. And the thing that we're supposed to notice is that what I got here is the same thing as the original integrand, except I have replaced the t with this upper bound of x. So, based on that example, we might guess that the same thing will happen here when we differentiate this integral. We're going to get the same thing. We're going to get the integrand again, but with the t replaced with x. And in general, this is the fundamental theorem of calculus part 1. If we differentiate the integral from a constant to x of little f of t, we get little f of x. Or in other words, if this is capital F of x, its derivative is little f of x. Okay, so question 2 is similar, except now instead of having just an x in the upper bound, we have an x squared. But we can use the same strategy of applying the fundamental theorem part 2, which tells us to find an antiderivative, and then plug in the bounds. And subtract. Now capital F prime of x is the derivative of sine of x squared minus sine of 4. And here we get to review the chain rule. The derivative of sine of something is cosine of that thing times the derivative of that thing. And the sine of 4 is a constant, so it goes away. Okay, so now, this time we didn't quite just get the integrand with the t replaced with x. Well, we got the integrand with the t replaced by the upper bound, cosine of x squared, but we also got a factor of x squared, which came about as the derivative of that upper bound of x squared. So, I might guess that in this example, I'm supposed to end up with the natural log of sine of x, which I've obtained by taking the integrand and replacing the t with the upper bound. But I should also expect to get a factor of cosine of x, which is the derivative of that upper bound, sine of x. So in general, the derivative of the integral from 0 to g of x of f of t dt is going to be the integrand with the upper bound substituted in times the derivative of the upper bound. And if this reminds you of the chain rule, the chain rule is exactly why this is the way it is. To see that, let's define capital F of u to be the integral from 0 to u of f of t. Then well, then the integral from 0 to g of x would be capital F of g of x. And I'm supposed to think about the derivative of this thing. So if I differentiate, the chain rule says this is capital F prime of g of x times g prime of x. And what's capital F prime? Capital F prime of u is just f of u. That's the conclusion of question 1 on this activity. When the upper bound is just the variable, no g of u, no u squared, just a u. When you differentiate, you simply replace the t with a u. So there we go. So the point is, if you believe this, then the chain rule tells us that this is what we get when the upper bound is something a little more complicated than just an x. Question 3 asks us to think about what happens when the variable is in the lower bound instead of the upper bound. we're differentiating the integral from x to 0 of f of t dt. We've seen this idea a couple times today already. I can switch the bounds if I throw in a minus sign, but minus signs can come outside of derivatives. And this is something I know how to think about. That's the results of question 1. We simply have x in the upper bound. So this gives us little f of x. But we also have this minus sign. So the overall effect of having an x in the lower bound instead of the upper bound is that we do just substitute that x into the integrand, but because it was in the lower bound, we end up with a minus sign. That brings us to question 4. We are attempting to differentiate the integral from 3x to x squared of sine of t dt. And the hint here is to break this up into 2 integrals. To integrate from 3x to x squared, we can first integrate from 3x to 0, and we can then integrate from 0 to x squared. And we know how to handle both of these. For the first one, I'll flip the bounds and add in a minus sign so that the variable is in the upper bound instead of the lower bound. And that's going to give me a minus 3 times sine of 3x. That minus sign is coming from there. I plug the bound, the upper bound, into the integrand, and I also multiply by the derivative of that upper bound. And the same thing happens here. I plug the upper bound into the integrand, and I multiply by the derivative of the upper bound. So if you write out a general formula for what's going on, you're ending up with f of b of x times b prime of x. And then from the lower bound, you get a minus f of a of x times a prime of x. If you write this out for this specific example, where this is f of t, that's a of x, and this is b of x, you'll see that you do in fact get this. Okay, that I think is all I wanted to say about these accumulation functions in the Fundamental Theorem of Calculus Part 1. So let me pause here and ask if there are any questions. Okay, another topic that I wanted to talk about is Riemann sums and integrals. You might remember from earlier, before break, we did some problems where we computed an area by writing it as a limit of Riemann sums, by finding the area using n rectangles approximately, and then taking the limit as n goes to infinity. It was a lot of work. There were a lot of steps, a lot of algebra, and that is not the sort of thing that we would ask you in a final exam. But what you could see on a final exam is we could give you a definite integral, and we could ask you to write it as a limit of Riemann sums, just not to evaluate the limit of Riemann sums. Or you could see the reverse. We could give you a limit of Riemann sums and ask you to tell us what definite integral that limit of Riemann sums represents. So let me show you some examples. I'm just going to write down a random integral. Let's say the integral from pi to 3 pi of cosine squared of x with respect to x. So let's express this integral as a limit of Riemann sums. So the Riemann sum is the sum of f of some x value times delta x, where delta x is the width of each rectangle. So if we're integrating from a to b, that's a total width of b minus a. If I divide that into n pieces, the width of each piece is b minus a over n. Now xk, x sub k is the x-coordinate of the kth rectangle. What exactly that is depends on whether you're doing a right Riemann sum, a left Riemann sum, or a midpoint Riemann sum. For a right Riemann sum, this is going to be a plus I times delta x. The point is that if I have a bunch of rectangles, the x-coordinate at the right endpoint of the ith rectangle is, well, for the first one, that right endpoint is at a plus the width of one rectangle. And for the second one, it's a plus the width of two rectangles. For the third one, it's a plus the width of three rectangles. So the ith right endpoint is a plus the width of I rectangles. The left endpoint is a plus I minus 1 times delta x. The point being that you just go one fewer rectangle to the right. So the left endpoint of the third rectangle is right here. That's a plus, not 3, but 2, only 2 rectangle widths. And for the midpoints, it's right between I and I minus 1. It's I minus 1/2 times delta x. Right? For example, the midpoint of the third rectangle is a plus 2.5 rectangle widths. That's 3 minus 1/2 rectangle widths. Okay, so the integral that we were looking at was the integral from pi to 3 pi of cosine of x squared to get an integral, we don't just take the Riemann sum, we take the limit of that Riemann sum as the number of rectangles goes to infinity. So I'm going to take the limit as n goes to infinity of this Riemann sum. And it's f of xk, but my function was cosine of x squared. So I've expanded out what the f is, but I have not yet expanded out what xk is. And I'm also not going to expand out delta x just yet. Okay, so I took the expression for the Riemann sum, I said what f is, and I took the limit as n goes to infinity. So let me just point out, I'm using the right Riemann sum. It does not matter which of these three Riemann sums you use. You will get the same result either way. These Riemann sums are not all equal to each other, but when you take the limit as n goes to infinity, those limits are going to be equal. If this were a multiple choice question, which I'm pretty sure at least one of the practice exams on Canvas has a multiple choice question like this. If this were a multiple choice question, we would probably have to tell you which of the three Riemann sums to use, so that the expression you write down is one of the multiple choice answers. Okay, so I'm just going to simplify this, or rather expand out what xk is. So xk is a, which is pi, plus plus I times delta x. And then times delta x. The last thing that I'm going to do is say what the delta x is. Remember, delta x is b minus a over n. So delta x is 3 pi minus pi, that's b minus a, over n, which is 2 pi over n. So this is the limit as n goes to infinity of the sum from I equals 1 to n of cosine of pi plus I times 2 pi over n times 2 pi over n. So you should be prepared on the final exam to look at an integral and write out this limit of Riemann sums. But we would not ask you to evaluate this. In fact, if you ever were asked to evaluate this, you should write it as a Riemann, or as a definite integral, and then use the fundamental theorem of calculus. Admittedly, that would be challenging here. I don't actually know what an integral, or what an antiderivative of cosine of x squared is. I'm just going to Google, because I'm curious. Yeah, cosine of x squared does not have an antiderivative in terms of functions that you've probably heard of, elementary functions. I'm looking at Wolfram alpha, which is telling me that it has an antiderivative in terms of a function called the Fresnel C integral. So basically someone just made up a name, I think, for this antiderivative. Okay, so you could also be asked to go the other way. You could be given something like this, and then be expected to write it as a definite integral. Let me show you an example. In order to do that, I'm going to write down a definite integral. And then I'm going to write it as a limit of Riemann sums, and I'll see if we can convert it back. Okay, so here's my example. The limit as n goes to infinity of the sum from I equals 1 to n of 1 plus I times 3 over n squared plus 3 times 1 plus I times 3 over n plus 2, all of that times 3 over n. So we're going to express this as a definite integral. Now this is maybe the scariest looking problem you'll see in all of calculus, this sort of problem. But it's really not so bad. Mainly because we're not trying to be mean. We're trying to be helpful here. We're going to actually, when you see this 3 over n, right, we're gonna put the delta x here. We're gonna make it look like what you expect. A sum of a function and a delta x. Okay, now multiplication is commutative. You might see the 3 over n at the beginning instead of the end. But if you see a number over n being multiplied with a bunch of other stuff, right, that's going to be the delta x. Okay. So what other pieces do we recognize? I see this 1 plus I times 3 over n. I already know that that's delta x. And I also know that I should expect to see an a plus I times delta x. In the previous example, that looks like pi plus I times 2 pi over n. But here, I'm seeing 1 plus I times 3 over n. I already know this 3 over n is the delta x. So this is going to be my a plus I times delta x, which is, that's the xi. Oh, sorry, I just realized I've been using i's and k's interchangeably. So everywhere that I wrote a k, that should probably just be an I. Okay, so this 1 plus I times 3 over n, that's my a plus I times delta x, which is xi. So I know that the whole expression is going to be the sum of f of xi times delta x. Here's the delta x. So this whole piece should be the f of xi, so that I have f of xi times delta x. Okay, so what do I know? Well, if this is the a plus I times delta x, a's got to be 1. But that also tells me what b is, because if 3 over n is my delta x, and delta x is b minus a over n, then 3 has to be equal to b minus a. But a was 1, so b is 4. Right? If I integrate from 1 to 4, that's a width of 3, so delta x is going to be 3 over n. And then if this is all my f of xi, I see that f of xi is xi squared plus 3 times xi plus 2. So f of x will be x squared plus 3x plus 2. Well, once I know the function and both of the bounds, I know what the integral is. This expression here is representing the integral from 1 to 4 of x squared plus 3x plus 2 with respect to x. So that's how you convert a limit of Riemann sums back into a definite integral. Look for the delta x. It's going to be some number over n. Everything else inside the sigma then had better be the f of xi. Identify that f of xi. The f of xi has an a in it. An a plus something. So that's the a. Let me once again pause for questions, and then we'll talk about the final topic for tonight. which will be L'Hopital's rule. All right, L'Hopital's rule. I'm just going to do some examples. And I have not prepared any examples. I just opened a calculus textbook that I have to the exercises in the section on L'Hopital's rule. And I'm just going to pick out the ones that look interesting to me and do them. And I'm doing problems that I haven't worked out beforehand, not because I was too lazy to prepare, but because I think it's actually maybe more beneficial for you to watch when I'm doing a problem that I haven't worked out before, because then you can see my actual thought process as I am solving these problems for the first time. So, okay, here's what looks like a good first problem. The limit as x approaches 0 of x minus sine of 2x over the tangent of, just the tangent of x. Okay. Now, on the final exam, if you see a limit, you're not going to be told that it's a L'Hopital's rule problem. You're just going to probably get a bunch of limits somewhere on the exam. And the first thing that you should always try when you see a limit is direct substitution. If I try to substitute in 0, I get 0 minus 0 over 0. 0 over 0 is undefined. So that does not mean that the limit does not exist. Usually when you get 0 over 0, well, I guess what I mean to say is a lot of really important and interesting limits are 0 over 0, even though the limit exists. So the limit might still exist here. Trying direct substitution, though, also has the benefit that it tells us that this is a 0 over 0 indeterminate form, which means that we can use L'Hopital's rule. Very important to check before we use L'Hopital's rule that we have a 0 over 0 or an infinity over infinity indeterminate form. So I'm going to use L'Hopital's rule and differentiate this. It'll give me 1 minus 2 cosine of x over secant squared of x. 2 cosine of 2x. Now I have a new limit. As always, I start out by trying direct substitution. If I plug in 0, I get this, which is, well, the cosine of 0 is 1. And the secant of 0, that's the reciprocal of cosine of 0. Cosine of 0 is 1. The reciprocal of that is also 1. And when I square 1, I still get 1. So this is minus 1 over 1, which is minus 1. Okay, so the limit is negative 1. Alright, let me find another problem that looks promising. I want one of a different variety where, oh wow, I see. This book actually has a section for 0 over 0 indeterminate forms, and then it has a separate section for all the other ones. I was looking at a section of just 0 over 0 problems and trying to find something besides 0 over 0. So maybe just do a couple more of these. This one looks fun. The limit as x goes to 1 of ln of x squared over x squared minus 1. Now when you try direct substitution, you plug in 1, you get ln of 1, which is 0, over 1 minus 1, which is 0. So we can use L'Hopital's rule. The derivative of ln of x squared is 1 over x squared times the derivative of x squared. And in the denominator, the derivative of x squared minus 1 is 2x. Now these 2x's cancel. That's nice. We're left with the limit as x approaches 1 of 1 over x squared. Direct substitution gets the job done here. This limit is 1. Besides L'Hopital's rule, this is also just a nice little review of some derivatives. Ooh, this one looks fun. Let's look at the limit as x approaches 0 from the right of 7 to the root x minus 1 over 2 to the root x minus 1. This is once again 0 over 0, because when I plug in 0, the square root of 0 is still 0. 7 to the 0 is 1. Anything to the 0 is 1, so I get 1 minus 1 on the top. And at the bottom, 2 to the 0 minus 1 is 1 minus 1, which is 0. So we can apply the hospital rule. And we're going to get the limit as x approaches 0 from the right of, okay, the derivative of an exponential. Let me remind you, the derivative of a to the x is a to the x times the ln of a. So the derivative of 7 to the root x is 7 to the root x times the ln of 7. But it's not just an x that I have in the exponent. The chain rule says I also need to multiply by the derivative of root x, which is 1 over 2 root x. And then, of course, when I differentiate the minus 1, it goes away. In the denominator, I have 2 to the root x times the ln of 2 times 1 over 2 root x. Now these 1 over 2 root x's cancel, which is nice. And actually at this point already we're able to use direct substitution. So we end up with the ln of 7 over the ln of 2, which, just for fun, we could also rewrite as a single log. It's a rule of of logarithms. That's equal to the log base 2 of 7. Okay. So that was some 0 over 0 examples. Let me flip over to the other indeterminate forms and see what fun problems we can find there. Wow, it's so hard to choose. There are like 40 problems here. Ooh! That one is fun. I will definitely do that one. But it's number 40, so let's maybe work our way up to that one. Okay. I'm looking at the limit as x approaches pi over 2. Of 3 times the secant of x plus 5 over the tangent of x. Now this is tricky, because this is not even an infinity over infinity. Right? The limit as x approaches pi over 2 of the tangent of x does not exist. And it's worse than just being infinity or negative infinity. It's infinity as you approach from the left, and negative infinity as you approach from the right. So I think we're going to need to look at the one-sided limits. This is a good general strategy. You won't see anything as complicated as this on the final exam, but again, I think it's valuable to do harder problems as you're preparing, because it'll make the exam seem not quite so bad. But also, right, these harder problems tend to require us to synthesize a lot of different concepts. So an important idea, even if you don't use it on something quite this complicated, an important idea to be aware of is when you're trying to deal with a weird limit, it's very helpful to look at the one-sided limits, because one-sided limits are easier. So we're just going to look at what happens on the right and the left. So let's look first from the left. Okay, so the tangent of x is approaching infinity as x approaches pi over 2 from the left. Secant, well, secant is the reciprocal of cosine. What's cosine doing as we approach pi over 2 from the left? Cosine of pi over 2 is 0. If I look at the graph of the cosine function, as we approach pi over 2 from the left, cosine of pi over 2 is approaching 0 from above. So when I take the reciprocal, what is secant doing? It's approaching positive infinity. And 3 times something approaching infinity plus 5, that's still approaching infinity. Okay, so this is infinity over infinity. It's an infinity over infinity indeterminate form. So I can use L'Hopital's rule. The derivative of secant is secant x times tangent of x. The derivative of 5 is 0. The derivative of tangent of x is secant of x squared, or secant squared of x. That makes me happy because the secant was causing problems. Right, the secant, that was going to infinity. So I'm glad to see one of these secants cancel. So I have tangent over secant. What to do about that? Well, you'll notice if I plug in pi over 2, well, I can't. It's undefined. This is still an infinity over infinity. But before we do L'Hopital's rule again, let's actually just see if we can simplify this at all. So I'm going to write this as, I'm going to write that tangent as a sine x over cosine x. And secant is 1 over cosine x. And the cosine x's cancel. Canceling is a little bit weird. The easiest way to see how to do this is to multiply by cosine x over cosine x. So when you multiply this cosine with that, it's a little more obvious that those cosines cancel. And then when you multiply 1 over cosine x with cosine x, you just get 1. So what am I left with is just 3 sine of x. And whenever I have a new limit, I try direct substitution. Sine of pi over 2 is 1. So we get 3. Now I'm just going to claim that the other limit is similar. I will leave this for you to think through the details, but I believe what happens is you just get negative infinity over negative infinity, so you can still use L'Hopital's rule, and then the calculation should look exactly the same. Denali Dice, do I stream the subject often? I've been streaming these review sessions for calculus in the last couple of weeks. This is the third one I've been doing. And just as we're leading up to the final exam, which is a week from today. Okay, so that was an infinity over infinity. Let me do something else. One of the other indeterminate forms. Let's do the limit as x approaches 0 from the right of 3x to the x squared. Thank you for the follow, Denali Dice. So what's going on here? As x approaches 0 from the right, 3x is approaching 0, x squared is approaching 0. So this is a 0 to the 0 indeterminate form. Now, I said earlier in the stream that anything to the 0 is 1. That actually wasn't even very long ago. That was when we were doing this problem. Anything to the 0 is 1, unless that thing is 0. 0 to the 0 is an indeterminate form. Now, whenever we see an indeterminate form with an exponent, the trick is to take the natural log. And we've seen that trick other times too. For example, when we're differentiating something like x to the x with a variable in the numerator and the exponent. The trick there is to set y equals x to the x, take the ln of both sides, the point being that the exponent of an x can come outside of the integral, and then you do some implicit differentiation. So it's just a recurring theme. When we have exponents, taking the natural log often helps. So we're going to look at the limit of the ln of 3x to the x squared. And just to be clear, these are not the same thing because this one has an ln. Adding the ln does change the problem. So the x squared comes outside of the ln. And now what's going on? As x approaches 0, this is approaching 0, 3x is approaching 0 from the right. Ln of something approaching 0 from the right, that's approaching negative infinity. Because the ln graph looks like this. It has a vertical asymptote at x equals 0. As the input to the ln function, which in this case is 3x, approaches 0 from the right, that y value, the ln of 3x, is approaching negative infinity. So this is a 0 times infinity, or I guess a 0 times negative infinity, indeterminate form. 0 times infinity is still indeterminate. But we can convert that we could actually convert that into either 0 over 0 or infinity over infinity. The point is that we're going to put one of these things in the denominator, although to put it in the denominator we have to take the reciprocal. Multiplying by x squared is the same thing as dividing by 1 over x squared. Now, you could also put the ln of 3x in the denominator. I just think this is probably going to be harder because we're going to have to take the derivative of 1 over ln of 3x. So just because we have to differentiate, I think that's going to be a little more complicated to deal with. So I'm going to do it this way. L'Hopital's rule says, oh, well, let me just also point out, this is a negative infinity over infinity. Ln of 3x is still going to negative infinity. 1 over x squared as x approaches 0 from the right. This is approaching, that's approaching infinity. I'm being very careful to check each time that L'Hopital's rule is applicable, because if it's not, you get the wrong answer. Okay, the derivative of ln of 3x is 1 over 3x times the derivative of 3x. The derivative of 1 over x squared is minus 2 over x cubed. And the easiest way to do that is to convert this to a negative exponent and then use the power rule. Okay, so these 3's cancel. And I'm left with 1 over x in the numerator, and then when I divide by a fraction, it's the same thing as multiplying by the reciprocal of that fraction. So this is minus x squared over 2. What do I do now? I try direct substitution, which gives me 0. 0 is not the answer, though, because we have to remember we were asked about this limit, and we did a different limit. We did a different limit, which was easier because it had an ln inside there to help us out. Fortunately, once we know this, we do know the original limit, because if we took the ln, then to undo the effect of that and get the correct answer, we undo that by exponentiating. So if I get 0, I raise e to the 0. Oops. And that gives me 1. So this is an example of how to handle an indeterminate form with an exponent, which could be 0 over 0, 0 to the 0, or 1 to the infinity, or infinity to the 0. And it also shows us how to handle a 0 times infinity indeterminate form. I think I'm going to do one more example because I saw a really cool looking problem that I can't resist, but then I think we'll wrap up. So I want to look at the limit as x approaches 1 from the right of the integral from 1 to x of sine of t dt over x minus 1. An integral inside a limit. Okay, what's the first thing you try? Direct substitution. That strategy doesn't change just because we have an integral inside the limit. We're still going to try direct substitution. I'm going to try plugging in 1 for x. And this integral is very easy to do because it's an integral from 1 to 1, which is guaranteed to give you 0. There's no width to this region. There could not possibly be any area. And 1 minus 1 is 0. So we have a 0 over 0, which means we can use L'Hopital's rule. L'Hopital's rule says we should take the derivative of the numerator and the derivative of the denominator and this sort of derivative is exactly the thing that we were looking at earlier with the fundamental theorem of calculus part 1. And when we differentiate this, all that we need to do is replace the t with an x, which is to say we're substituting the upper bound into the integrand. And in the denominator, the derivative of x minus 1 is 1. Now that I have this new limit, I'm going to try direct substitution again. I plug in 1, and that works just fine. I get the sine of 1. I don't know what the sine of 1 is. That's not an expression I can simplify. 1 radian is not one of those nice angles where I know the values of the trig functions. But sine of 1 is the answer. So it looked scary. It had a limit and an integral, but if we just keep our cool, try our strategy of direct substitution, we'll pretty quickly see that it's a 0 over 0. So we use L'Hopital's rule. I need to take the derivative of an integral. That's the fundamental theorem of calculus. And there we go, sine of 1. All right, let's call it a night. I'll stick around for just a minute in case anyone has any questions. Otherwise, I'll probably plan to do one more review session later this week so I can talk about some of the topics from this week, like U substitution, maybe areas between curves. And as always, if anyone has any topics that you'd like me to talk about, feel free to let me know in the chat or send me an email anytime between now and the next review session. I'd be happy to cover anything that you'd like to see. All right, since I don't see any questions, thanks for joining, and I will see you next time.